radius 1 sitting on a horizontal plane. So let me try and draw this. Okay. We know that the radius, here, I'll just draw it out this way, is 1. Okay, the cylinder is inside of this hemisphere. It's sitting so that its base is centered at the center of the sphere. So we're going to try color. I don't know if this will show up very well. Okay, so there's the base. I don't know how big it is, but just for example, shares the same center, and then it sticks up just perfectly so that its top circular rim is just touching the edge of the sphere all the way around. And we are trying to figure out the radius and the height of the cylinder that maximize its volume. So let's say this is the radius of the cylinder and this is the height of the cylinder, and we want to maximize volume. So let's say V is the volume of the cylinder. Okay, so just to make sure we're seeing this, this is kind of an in-between. We could make the radius really close to 1, and what would happen then is our cylinder would be really short, or we could make the radius really close to 0 and get the height taller, almost 1. So those are kind of the extremes, and we're looking for something probably somewhere in the middle that gives us the biggest possible volume. Okay, so volume of a cylinder is pi r squared h, and I didn't write it out in words because I've already labeled r and h exactly like that, but you certainly can. So actually our big challenge here is just we have too many variables. How do we get rid of one? And it's actually not that hard, but it can be really hard for people to spot. So probably you can guess that it has to do with the hemisphere. We haven't used that at all. So it goes back to that question, if I choose an R, do I get to choose any H that I want? And the answer is no. Once I choose an R, the H is determined by the sphere. So actually, you could do this by finding an equation for the surface of the sphere, but we don't even have to. We can get it a different way. If you're ever having trouble with a 3D shape, something to try is to try and make your picture 2D. So imagine slicing this in half right down the middle. Our hemisphere will look like half a circle, and our cylinder, if we look straight on, will just look like a rectangle. And we know that this is R, and we know that this is 1, and we know that this is H. So still, we need to somehow get this involved. It's the 1 we need to get involved. This radius 1 is the key feature of the sphere. So what you actually need in here is a triangle, but it's hard for people to spot just because a lot of people will label the 1 here and then thinks that's the only place that they get it, but this actually has to be 1 as well. The whole idea with the sphere is anytime you start from the center and go anywhere on the outside, it's 1 away. So the relationship between R and H is actually just a Pythagorean theorem. R squared plus H squared equals 1. So this cutting 3D shapes down the middle and just looking at a cross section is a really good trick. Okay, so we could keep either variable. It doesn't really matter. We're going to need both in the end. And what I'm humming about is that there's an R squared in this formula. So we could actually be kind of clever and say that R squared is the same as 1 minus H squared, which means if we want volume to be a function of H, we take the pi, we multiply it by a 1 minus H squared and an H, which means distributing in pi H, we get pi H minus pi H cubed. Okay, so there's our function. That's usually the hard part. We can think about reasonable domain here. So the domain, this is H's. H is on, okay, so the smallest H could be is 0. It's a bad choice. Our cylinder flattens out into a circle, but that's the minimum. The biggest H could be is 1. Once again, a bad choice. Our cylinder has now just become a straight vertical line, but those are the extremes. So those are my endpoints. I'm going to need a V of 0. I'm going to need a V of 1. And then critical values, we're going to get derivative of pi h is pi, the derivative of 3 pi h cubed, pi h cubed is 3 pi h squared. And if we set that equal to 0, I'm going to add the 3 pi h squared. I'm going to divide by 3 pi, which actually cancels out a pi. You're left with 1/3. Make sure you don't lose track of that 1, which means that h is plus or minus the square root of 1/3, which is the same as 1 over the square root of 3. Square root of 1 is just 1. I'm not interested in the negative h value, so I actually just get to throw it away, and I really just need to check positive 1 over root 3. So back to my formula, when h is 0, v is 0. When h is 1, I get pi minus pi, which is 0. And when h is 1 over root 3, let me do just a little scratch work, I get pi over root 3 minus pi 1 over root 3 cubed. Okay, so it's going to be a root 3 cubed, which looks really messy, and you can check with the calculator if you need to. Root 3 cubed is bigger than root 3, which means this fraction is smaller. So that's greater than 0, and that's really all I need to know. It is, in fact, my maximum. If it's positive, it's a max. You can get a decimal even for that if you want. Just make sure you check. So going back to the question, it was find the radius and the height. So now I know that the height should be 1 over root 3. And do we have units? No. The radius, we'd have to go back to this formula. So we could say for our specific answer, r squared is equal to 1 minus the square of this. Square of 1 over root 3 is 1/3. So r squared is 2/3, which means r is root 2 over 3. Again, we can ignore the plus minus because radius shouldn't